Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yogashri Pradhan, and with me here today, I have Faye Liu from RevoChem. Today, we're going to discuss the paper URTEC 2902, and the paper description is written below in the YouTube description and in the Apple Podcast description. I'm going to talk a little bit about Faye before we go ahead and pepper her with questions. Dr. Faye Liu is the founder and CEO of Rebel Chem, a technology company with patented lab procedure and data analytics tools in high resolution, high fidelity geochemical fingerprint data from the oil. She's worked for ConocoPhillips as a senior geochemist for 6 years and pioneered the application of geochemical data as a reservoir engineer monitoring tool. She then founded RevoChem with her husband, Dr. Jiang Wu, who's a biochemist with many years of experience working in the medical field. Today, they adopted and optimized several chemical analytical methods from other disciplines, including medical, food, and environmental areas over modernized geochemical analysis and data analytics using geochemical data. Faye has used her experiences using geochemical fingerprinting technology over 1,000 wells across various basins, including Permian, Eagle Ford, Montney, Gulf of Mexico, Scoop Stack, Bakken, and Vaca Muerta, resulting in improved reservoir economics through optimization of stacking and spacing, completion design, conventional reservoir compartmentalization, as well as communication and EOR options. She holds a PhD and MS in geochemistry, both from the Indiana University Bloomington. She holds a BS in environmental engineering. She has first authored over a dozen peer-reviewed papers, which have been cited over 600 times globally. She also serves on the advisory board for the IU Earth and Atmospheric Sciences Department and recipient of IU 20 under 40 for 2020. So congratulations, Dr. Faye Liu, and welcome to the podcast.
Thank you. Thank you. It's a great pleasure to be here. I've heard so many great words about your podcast. I'm so glad I can be part of it.
Awesome. Well, you talked a little bit about RevoChem in the bio, but I wanted to hear from you. Could you expand upon what exactly RevoChem does for viewers and listeners?
Yes, absolutely. So like you already did a very good introduction about me and the background. So essentially, we are a geochemical fingerprinting technology company that we use information from the oil, whether it's directly from the produced oil or the oil extracted from cuttings or core, to help understand. It's a tool both for the reservoir characterization to understand key reservoir properties, and most importantly, to understand the subsurface fluid flow in the reservoir as a reservoir monitoring and surveillance tools to understand the drainage of the reservoir as well communication.
Awesome. Thank you for that clarification and the explanation. Because we're talking about 2902, and I was really interested when I read the paper. In fact, when my colleague sent me the paper, and when I read it, I just knew I had to ask you way more questions than what the paper had. So I was wondering if you could walk us through the paper to orient our viewers and listeners.
Yes, absolutely. So that paper was published in URTEC 2020 with Diamondback. And actually, there's a follow-up presentation that we did jointly with Diamondback in the past WTGS conference symposium, actually in September 2021. So they give the later part of the story, how they use the results to actually optimize the landing and get better performance from their neutral well and able to reach out additional rock volume that was previously untouched due to the landing. So that paper have actually two parts of it. The first part of it, which is also our typical workflow, usually it starts with the static characterization that we collect cutting samples vertically. Usually it's at a frequency anywhere between 10 to 20 feet vertically, so that we can extract the oil from those cuttings to look at the oil fingerprinting to give us some of the key properties such as matrix permeability and oil saturation. So the reason we're able to get those reservoir properties from those oil data is because the oil actually reflects a lot of those rock properties. For example, when we pull out the rock from the subsurface to the surface, inevitably there's some light end lost in the oil. And we found a really good correlation that everything else equal, the more loss you have the light end, it corresponds to higher permeability. So based on things like that, we actually able to infer a lot of reservoir properties by interpreting the oil data from the cuttings or the core. So we built a group of what we call RCI, reservoir characterization indices, by interpreting the oil data from the rock. And it's PetroPapers really like that because it's an independent line of evidence. Usually they measure the rock and we measure the oil. And if it's matching each other, then it's another confirmation for those important reservoir properties. So that's the first part of it, to using those cutting samples to understand reservoir properties as a static characterization tool, and also to establishing the geochemical fingerprint vertically from those cuttings so that we know for each of the formation what it looks like geochemically, so that we can compare that and using those cuttings as a baseline to compare that against the oils. So once we have the oil put out, once we have the well put online, starting to collecting the oil samples, we can build a regression model based on those 2,000 plus compound information to correlate the oils back to the formation where it's coming from. What is really unique about our methodology is that traditionally the regular GC, which have been in the industry for 50 plus years, are only able to resolve less than 100 compounds from the same drop of oil. While we added another dimension of separation, so the gas chromatography become, instead of one dimensional, have another dimension of separation, so that compound with the same boiling point, which is what this first dimension separation is separating the oil, with the same boiling point are further separated based on its aromaticity, which means the ring structure. You have the straight chain, then you started to have folded structure and rings and double bonds. And this methodology gives us over 2,000 compound resolution versus the traditional less than 100. So that's a huge game changer. I also made an analogy as a geologist going from handheld microscope to the SEM. That's at first, most importantly, you have to be able to capture those fine granularity difference before you can do anything. I mean, if you don't have the right tool to be able to capture that fine granularity difference. And when we're talking about those unconventionals, those differences are much smaller than traditionally if you're talking about, the differences between those source rocks, such as, if you're comparing the difference, you're only happy about telling the difference between Wolfcamp to the Eagle Ford rock or to Avalon rock. Traditional method is fine. But if you wanted to tell the fine granularity difference between the upper part, the first 20 feet of your geomeal and the next 20 feet and the lower geomeal, those differences, particularly those more sandy reservoir with higher permeability, are definitely much smaller. Difference are definitely much smaller, that you really need those high resolution tool to capture that. So the second part of the paper is talking about how we use geochemical fingerprinting from the oil and correlate it back to the depths that are represented by those cutting samples, so that you get a quantitative zonal contribution where that oil is coming from for each of the timestamp for each of the well. We are looking at a concept called the drainage rock volume versus the SRV. So we are directly looking at the oil that end up in your, wellhead separator, become your revenue, instead of what's gets stimulated, you could generate much larger frac job. It may or may not support your flow, or may not be there for a very long period of time. So the drainage are, in my opinion, the most direct representation and linked to your well performance. And we're able to understand what is your drainage frac height and how that evolves through time. In that paper, we do have a well that's actually when the upper well was put online later than the lower well. So the lower well, when there's not a well stacked above it, so the upper well was not online yet, it's able to drain much more from the upper zone. But once the upper well is online, the lower well stopped seeing contribution from the upper zone. So it's very dynamic, and it's the resolution are very high resolution and sensitive. So it's reflect a very high granularity of information that can be impacted not just by the static geology, but also a lot of the operational events, such as nearby activities, well put online, or even well that are put on ESP before and after. It's all having an impact to its nearby well. So eventually, yeah, that's the second part, to understand what is your drainage frac height, what's the percentage that are coming from each of the zone. Because even if you're draining, let's say 300 feet, it's not equally contributing. You could, so we calculated P80 and P90 of drainage frac height, you could have 60-70% of your contribution coming from just that 100 feet. So having that very high fine granularity, and how that varies through time. Some of the fracture we see that in the early, so I always encourage people to grab sample as early as possible. We have over 1,000 wells in the Permian we're monitoring along with many other basins. The first 2 weeks of production, you always see so much going on. And if you miss that 2 weeks, you may come with a different conclusion. We find in the first 2 weeks, it have better correlation with if you have other tools such as microseismic, it's linked better with what gets stimulated, but afterwards, then it's dramatically changed due to other factors. Some zone are higher permeability, their TAP faster, and they may reduce their contribution to time. So it become, impacted by a lot of other factors. So that's in a nutshell what's in that paper.
Thanks for clarifying that, and also balancing the detail as well as the summarization of the paper. Really, really appreciate it. And when you were describing the paper, I remembered the sections that you're talking about. So I was just remember looking at the paper in my mind, and I was just going through, okay, she's on that section.
Yeah, it's a lot of content in that paper.
It is. Well, the first question I really wanted to ask in thinking about just the workflow is really, what is the reliability of shale cuttings for this analysis, especially when determining the reservoir characterization index that you talk about, and how much preparation must the operator do before your work comes in?
Yeah, so it's a very good question. We got that question a lot, because traditionally, people don't trust the cuttings because, most of the time it's a petrophysicist doing the analysis. And when you are from larger piece to a, very small cutting size, your pore structure change, and it'll change all the, the permeability, all those rock properties. However, if you think about it, oil molecule is smaller than the smallest cuttings. It's the size of the rock is not going to impact the geochemical fingerprinting information, those molecule information. A lot of very large operators, their initial project with us are to compare the core and the cuttings, and we've done that for many very large operators and to help them build the confidence. But I would say that so in terms of cuttings, to characterize as geochemically, there's no difference between as long as the same sample is there's no difference to the sample size, whether it's a core or cutting. To some extent, cutting works sometimes even better than core because it covers better heterogeneity. Like the core is a point, like you have that 1-inch core plug that's representing that 1 inch. The cuttings by nature, it lump a wider zone. So when we have operators who did interesting tests that if you collect the core at very high resolution and smooth that out, then you get the cutting signature, actually, the curve, because the cutting lump into a wider intervals. So in terms of the robustness of the geochemically from the cuttings, there's really no issues at all. We've done core, we've done cuttings, and we've done both core and cutting from the same well in multiple places. And I think as long as it's a apple to apple comparison, then it's fine. I mean, apple to apple means if the cuttings is a slightly wider interval than the core. We've done core, do a split and the other split to other petrophysics, NMR, and you get point to point perfect match. The cuttings is matching it, but it's sort of if you link two dots of the core, average it, that's what the cutting is saying.
Okay. And then for operators, they would need to collect those cuttings, and then would they also need to assign where exactly oils are located, or like where oils are located, and what is attributed to each section, and what kind of preparation must needs to do?
Yeah. So the cuttings are collected usually, well, I say usually, actually almost 100% time it's mud logger collecting it. And there's not much prep. We provide all the sampling kit. It's pre-labeled, everything, foam box and return shipping label, prepaid, everything needed, marker, tape, everything needed in a dump-proof, like we try to simplify as much as I being on the site and know how much things can be going on the site. So that sampling kit, we can provide that, and all you need to do is to collect the cuttings, put the depths on, and we ask if you could rinse it. That would be the best, if so that we can remove some mud. If not, that's okay. Just ship it back as soon as possible. We'll clean it right away. For the oil, we don't need the landing. We just let the oil itself to tell us where it's produced. Landing is never input. Our input are, and we try to keep it as independent as possible as well. Just it's just let oil tell us the story, because sometimes even if you land it in certain zone, it may not necessarily getting majority of its contribution from that zone. We've seen that happen in multiple places. But eventually it all balance back to where it's landed. Sometimes it's depending on different scenarios, so how the well up and below stacked. So we don't need any information in terms of landings. The only input used in the model is those geochemical fingerprinting information from the oil versus the cuttings.
Okay, thank you for that clarification, and thank you for mentioning just the ease of what operators have to do. It doesn't seem like it's that much. It doesn't seem like it's that much work in the paper. And you also mentioned this in the description, or when you were talking about the paper, or walking through the paper, about the 10 to 20 foot resolution. I just wanted to get some clarification for our viewers and listeners. Is that just for the vertical section, or is it also vertical and for the lateral section?
Yes, that's a very good point. It's only for the vertical. Yeah, unfortunately, we don't have the resolution laterally as we have vertically, because geology depositing this way, it's changing much faster vertically than it changing laterally. And also because we need to use a water-based mud cuttings, and in a lot of times after the curve, then it becomes oil-based mud. So we have much less usable lateral cuttings. However, we do have several pilots where we have water-based lateral cuttings, where you're definitely not at 10 feet, but a few hundred feet, you definitely see there's some variations going on. Not as frequent, as high as we can do vertically, but that's going on. And we do have a alternative product to understand lateral well communication that we just become available from earlier this year, called the similarity index, sort of not completely quantitatively, but because as I mentioned, the resolution is not exactly there, but semi-quantitatively to see between wells when you have different spacing or different completion styles, maybe A and B have more overlapped frac wing, and they're showing higher similarity from those lateral direction. So yes, what's mentioned in the paper is just on the vertical, more of a drainage frac height delineation. And after that paper become available, the similarity index on the lateral just become available from earlier this year. So that was not described in the paper, but it's coming on the hydraulic fracture conference in February in 2022. We have a publication with another Midland operator that particularly talk about that lateral part.
Thanks for mentioning that. I'll definitely have you back on this podcast for that paper.
That's great. Yeah, I'm very excited about that paper. Actually, it's the operator did an independent pressure test, and they have very comprehensive production data that where they see over communication, they actually see compromised performance, and it's a beautiful correlation that we found in that area.
Wow, that's awesome to hear.
Yeah,
I wanted to pivot a little bit on the data analysis portion of the paper and the resampling portion of the paper. What exactly is a blob, and then why is that the input data and the uncertainty analysis?
Yeah, sorry, well, 2-dimensional you call it peaks, and 3-dimensional it's called a blob. I don't know the very initial GC by GC guys decided to call it blob. I'm fine with that. So that's whatever term they use. Yeah, it's just because it's a 3-dimensional now, because it's a first dimension time, second dimension time, and third dimension is the intensity, which is corresponding to the concentration of that compound in the oil. So blob just means a peak, a compound. So that is the basis of all the calculation we're doing. So fundamentally, the oil composition, no matter where it's coming from, North Sea, Permian, Gulf of Mexico, it's including more or less similarly. You'll always find those 2,000 plus compound is consisting of very similar compound. However, when we say geochemical fingerprint, their differences are actually in the relative abundance. One compound versus the other compound, their ratios. So in this case, then it's the blob ratio. You compare, 1 methanepsine to 2 methanepsine. 2 compound ratio between different intervals can vary significantly. And the reason they vary significantly can be there are many reasons that lead to that. Some of that are coming from the source of it, the different deposit that's in different organic matters. Some are doing the migration. When oil migrated from kerogen-rich, some clay-rich zones, then certain hydrocarbons, mostly those chain structure, longer chain aromatics, have higher affinity for those kerogens and tend to accumulate in those source rock, and some straight chains are easier to move, tend to accumulate in the reservoir zones. And different mineralogy are also causing this a different, almost a sieving effect of certain compounds tend to accumulate in certain zones. And there are many different reasons that are causing those geochemical variation vertically. And that's what we're relying on to build those regression model. Yeah, that's, what's your second question? I'm sorry.
Just why is that the input data and the uncertainty in the uncertainty analysis? Like, why are blobs?
Okay. Yeah. So the uncertainty analysis is because when we measure the compound, there's inevitably some analytical error. Some are like 0.05% or whatever that is for different compound. So we just see what are those analytical error, what's their impact to your production allocation results.
Awesome. Thanks for that clarification. I also wanted to pivot to the results section of the paper, where there was variation by depth, and then there's reservoir characterization index, and then there's also oil in place in parallel.
Right.
There were some points where the RCI was high, but the oil and paste was low. So how do you reconcile that?
Yeah, so so the RCI, which is the reservoir characterization part, came after some initial time with Rebel Chem's foundation. That's when we started to interpreting the data. At first, it was the product was not there. At first, the cuttings only serve as a baseline for production allocation. However, as we dive into those thousands of compound, those data, we found that actually it corresponds, it's reflecting some of the reservoir properties. So we come up with algorithms and still continue improving it to reflect some of the key reservoir properties, such as oil saturation, some of the matrix permeability. And it's a measurement, so it's what it is. If it's high, it's high. If it's low, it's low. We always load the same amount of rock sample and look at the total oil extracted. If it's high, it's high. If it's low, it's low. And if it's have more loss, then it's a higher perm. It's what it is. So the RCI have really minimal interpretation. It's just measure the rock. That's how much oil in the rock, and things like that. So it reflect a static reservoir properties. And after we get the production allocation, because a lot of those reservoir behaviors can be partially explained by geological properties. For example, some of the zones, such as Geomill or Dean, those intervals, they are at lower absolute oil saturation when you compare it to other, source rock zones such as RevoChem. However, the reservoir quality index, which is the matrix permeability indicator, is very high, and so in that case, it's a balance, and we typically see that those zones become very productive. Because the reason can be many. Those are more sandy. I would imagine have lower residual oil saturation. Oil move more easily. There are many reasons. We're not trying to, we're not in the position to fully elucidate the why question, but we give the end result. This is where the end result is coming from, which each of the zone, and geology can play a key part of it. And that's a lot of time the only static data we have. When you're in the operator side, you may have a lot of other data that can be integrated to fully elucidate what is happening that are driving this different productivity and why a certain zone contributing more in the early time or later time, what are changed that are causing this behavior. So in terms of your question, why certain zone are high perm, certain high oil saturation, that part is just measurement. It's what it is. In an ideal world, you would want to see high saturation and high perm go hand in hand, but in reality, that does not always happen. And our purpose of coming back, linking the dynamic behavior, the drainage, to the static characterization is that so that we can find some hint of what are the key geological properties that are driving productivity, so that in the next well, because a lot of smaller operators, after they establish confidence in this, they just collect the cutting on site, overnight it, and this RCI can be generated really fast. So then they have a trained pair of eyes. Oh, I need to chase oil saturation in this area. It's a high oil saturation zone in this, I don't know, in a Geomill landing or in a lower Spraberry landing, are dominating the production. So that's what I need to chase. Or in another area, it's maybe the high reservoir quality zone are contributing majority of the production, so that in the nearby area, if I drilling in that landing, I wanted to fine tune my landing to chasing that high reservoir quality zone. So so that's what that how to sort of the workflow linking the static to the dynamic, so that it can also provide some guidance for the future well landing, even before you get your produced oil.
Thank you for that. And that's really helpful to know, because when you see those discrepancies, or at first I thought it was a discrepancy, that really makes you think about where exactly you want to land or how exactly you want to complete the well.
Yeah.
The other question I wanted to ask is, what are some practices you suggest and how often you take samples? And then how long in primary infill wells? And I know this paper specified Midland Basin, so I guess we can start with Midland Basin. But then I also wanted to know about the Delaware Basin and other shale plays, because we do have listeners that are in those areas as well.
Yes, absolutely. So there's the static cuttings or core, and there's the produced oil. For the static cuttings or core, the typical recommended sampling frequency is 10 to 15 feet vertically. And you probably wanted to sample 200-300 feet above and below your landing, just to cover all the zone that are potentially contributing to your production. And that 10 to 15 feet comes with a lot of trial and error, depending on different zone, how fast geochemically it change. And it still varies in different areas, different formations, different geological setting. However, we found 10 to 15 feet is a good, in majority of the play we've worked with, that's a good number to start with. In a lot of places, when you go beyond 20 feet, then using one sample to cover that 20 feet is just too much heterogeneity going on. And we started to see some models struggling with that. And in some of the areas, such as Powder River Basin, you have Turner, which sometimes is only 30 feet. If you could miss that entire interval if you collect every 30 feet. So I think and we have operator go very excited about this. When they have core, they can go in Eagle Ford there's 3 feet, 5 feet, and we started to see that's sort of pushing the limit of where we can confidently tell them apart geochemically. So I think every 10 to 15 feet, maximum 20 feet is a to the best of our knowledge, that's the best starting place. You may decide to go beyond that for, let's say you collect at that frequency for 200, 300 above and below, but you wanted to get some idea of what's above, which have much less probability of contributing significantly. You could space that out 50 feet or something, just to get some characterization of the zone above and below.
I see. Thanks for that clarification on that as well.
Absolutely.
Yeah. And it's good to know that that's a good baseline for other shale plays, and making sure you're covering the heterogeneity. I want to go back to the results section. What was the timestamp we were looking for the drainage frac and the height intensity? And then how long is that data relevant? And then did you ever get a chance to compare that to frac modeling?
Yes. So in that paper, at the time when we published it, it's still, the well is still under monitoring. At the time when we published it, I think it was 8 to 10 months of production that we have. The operator did an excellent job, capture the early samples. I think was in the beginning every twice a week for 2 weeks, and then weekly for another period of time, and then slowly spacing it out. And that is that's the monitoring time. And when we calculate the drainage frac height, we tend to suggest wait until you have about 3 to 5 months of production to have enough data to understand. Because if you only look at the first 2 samples, you could come up with much bigger number. While you wanted to understand the full story, then typically wells would stabilize at that 3 to 5 times for a 3 to 5 months period. Technically, every sample we can calculate the drainage frac height just to see where that 90% of the contribution is coming from. The vertical zone where cover 90% of a contribution, where it cover 80% of a contribution. Actually, Diamondback in that WTGS talk, which is on our YouTube website, that they shared, I think was 60 wells where they did microseismic, and they found a very good match between the P90 drainage frac height from our analysis to the microseismic. So we tend to use the P80 because the P90 essentially are just screening out the error bars, because there's a few percent error bar in each of the sample, and we report that both the P80 and P90. The P90 is essentially screen out error bar. However, the P80 is to further screen out the one-off events. When you look at the life of well, you could have one day that's get a frac hit, then you certainly see a shoot up of a frac height, and then next day go back. So we typically recommend to use the P80 to screen out, both the P90 screen out the error bar, but the P80 further screen out the one-off event. And the P80 is definitely, noticeably smaller than the P90. And yeah, so I think that is a very, very nice data set, sort of, and not just looking at one well or two well. It's a statistically meaningful number of wells where the operator was able to build confidence using a more of a traditional tool to compare.
Awesome. And I'm glad that you mentioned about the corroboration or the correlation with the microseismic. I know I was thinking about frac modeling, and when I think about drainage height and drainage intensity and comparing that to what's been stimulated. So it's good to know that something else has also been corroborated with.
Yeah. I think the Frac model is definitely a very, we have, that has also been done with many different operators, and there are different type of Frac models, right? And in general, they most of them use that as an important input to constrain their Frac model. That's from what I was being told to help constrain how much that Frac can go.
Oh, wow. Well, I'm glad to know that I wasn't just imagining things about modeling. There are people there are operators.
Yeah. There are a lot of them actually using that way. Yeah.
Awesome.
Yeah.
Well, I have peppered you with so many questions, but I wanted to ask you this one last set of questions. And hopefully this brings home everything that we've talked about. But really, what is the significance of having the excruciating detail of fingerprinting and uncertainty analysis compared to traditional geochemical analysis? And then what are some applications to this workflow that we haven't seen before in this industry?
Yes. My background is I'm a geochemist. My PhD in geochemistry, and I started a program called time-lapse geochemistry when I was at ConocoPhillips, and that was using traditional, regular, readily available method GC that the industry has been using for 50 plus years, and I only can do that much if you are at the resolution that, just as, a picture at the low resolution, or the microscope handheld, that's the resolution you have. And when you move on to unconventionals, you have a very different challenge. Traditionally, geochemist's job is to serve the exploration. Our job is to find the oil, find the salt rock, how it gets into the reservoir. So our job is only to tell the difference between different salt rocks. So all the tools are designed to serve for that purpose. When you are in an unconventional reservoir, every feed matters. They wanted to know not just how much is coming from WolfCam versus coming from another salt rock way above it. But within the WolfCam, what about the upper, middle, lower, which part of it? Because now the wells are stacked so close to each other, spaced, and that have a different requirement and different application that really needs to go to the next level. So that's the reason that I decided to quit my job and start my own company, because I felt that if I don't do it, I felt that I'm delaying the industry for years of doing that, because I've in and out doing that for years. I know exactly the pain point. So it needs to be fundamentally changed in terms of the way that the resolution of the data, so that you can tell and capture that fine granularity difference. So that's why I quit my job, and my husband is a biochemist. He worked in medical center, PhD in biochemistry. We started talking, and there are other tools that have been used in other industry that have the resolution, but just need to be adopted to our application. So that's our story. Of RevoChem, how RevoChem started, and I'm very glad it worked out, and it worked out very well. And a huge portion of that is also data analytics. So when you are dealing with thousands of compounds, and each of the blob are consisted of tens of thousands of data points that form that peak. So it's tremendous amount of information, not just in the total volume, but in the shape of it, in the position of it. And we actually have, the data team is the largest team in a company. We have more data scientists than anybody working in the lab and all that. So it's really modernized both the analytical tool and the data analytics tool to effectively pull out the information from those valuable data. So if you look at the regular, I actually have a example that I'm happy to share with you at a different time. That in the regular GC, there are two intervals that you cannot tell them apart. However, using the high resolution, you can clearly tell them apart. So if that information is not captured in the first place, then you cannot do anything with it. You have to have the raw data that capture at the granularity to be able to see the difference. So that's fundamentally how we differentiate and essentially build on the pain point of previous methodology. That's actually the story of RevoChem. And so we are keeping on exploring new ways of utilizing the data. I think we're only at the beginning of utilizing this type of data because the industry have many years of experience using physics-based data, such as pressure data, temperature, seismic, acoustic, those type of data. There are limited number of them, and I think with the fiber optics and there's already huge progress on that. And however, we're just at the beginning of utilizing chemistry data, and if you think about it, it's the most direct data to measuring. The oil gas industry is relying on the oil is your product, and to understand better about your product and what's in it, and the information carried in there. Honestly, a very low ticket price for thousands of compound information that we are now just interpreting it against the vertical cutting to understand the drainage. But there are many different ways to utilizing that information to understand its phase behavior, to understand well communication. And that's our new product, the similarity index to understand well communication and lateral well communication, as well as frac wing overlap. That's another way to understand interpreting the data. And I think we're just really at the beginning of utilizing this powerful data type. And we're in a data era, and I think, how can you overlook such a valuable data set that's very inexpensive, and we're, the industry, the shale industry, are now under tremendous financial stress to do everything the most cost-effective way. I mean, this is Probably the cheapest way to monitor a reservoir. There's no installation of anything. There's no interruption of performance of your well production. You don't need to install those fiber or those tracer or anything. It's just a separator room temperature pressure sample. So it really, I think the logic philosophy that behind geochemical fingerprinting is really in line with what shale industry is doing: flexible, cost-effective, and data-driven.
Awesome. Well, thank you so much for being on the podcast, Faye, and letting me pepper you with questions.
Absolutely, it's my pleasure. Yeah, it's such a pleasure to be on your podcast, and I hope your audience enjoy this session.
Awesome. Well, you heard it straight from Faye regarding all the questions that she's answered for URTEC 2902. Feel free to send me any feedback on who else I need to pepper with questions on this podcast. This is Yogashi Pradhan, and I'm signing off.